So in the last video, we explored what eigenvectors are, right? And these are vectors, or you could say directions that stay, that the direction doesn't change, but their magnitude changes under the effect of these linear operators, right? And remember, we came up with a definition, and what we're going to do in this video now is use this definition to come up with a process for actually finding all the eigenvalues and eigenvectors of a particular operator, or you could say of the operator's standard matrix, right? One and the same. So remember, this is what we came up with. This is our definition. So this is our matrix multiplication on this side, and then on this side we're saying that it's going to be equivalent to scalar multiplication. And just as a reminder, we don't want our eigenvectors to be zero, right? It's not that zero doesn't work, but they're not very interesting, right? So we want non-zero solutions to this. Now, one of the standard ways of solving equations where you have an unknown, in fact, there are two unknowns here, is to bring everything to one side of the equation and then try to factor. So let's do that. Let's do a little bit of vector algebra. Remember, these are just vectors, right? Yes, they're in a kind of a more abstract form, but these are just vectors. Let's subtract the vector lambda v from both sides. So then we would have that AV minus lambda v, and now on this side we have the zero vector, right? Because we've subtracted the lambda v. So what does this mean? Well, we now have a homogeneous equation, it looks like, right? A homogeneous system of equations, but now we have two terms that have a v in there. And again, another standard thing in algebra is like once you're finding like zeros of something, and you have multiple terms that have the unknown that you're trying to find, is you factor, right? So let's see if we can factor out the v. And then because of the properties of matrix multiplication, I can't just like put the v on either side. I have to keep it on the right side of this expression. So I have to put the v right there. That would leave the matrix A here, but then something strange happens because remember the lambda is a scalar, right? It's just a constant. And in terms of our matrix operations, what I now have in parentheses doesn't make any sense. I can't subtract a scalar from a matrix. So what do we have to do? We have to use that magic identity, which is basically the matrix version of the number 1. So we have to put the n by n identity right there. And now I can complete my equation, and here it is, right? So in other words, if lambda comma v is an eigenpair that satisfies this original definition, then it must satisfy this homogeneous system. But here's the thing. Since our eigenvectors need to be non-trivial, meaning I can't just have the zero vector as a solution, right? So here's our logic. So since the eigenvector can't be the trivial vector or zero vector, then what does this mean for this homogeneous system? It means that this coefficient matrix here can't have an inverse, because if it does have an inverse, then that inverse would just cancel out if we were to do pre-multiplication with our inverse, right? In fact, let me remind you of that key fact, right? If you have any kind of equation, homogeneous or not, right, linear system, if A is invertible, then you just say that X is equal to A inverse times B. But then again now, if B is the zero vector, right, so let me put a zero vector here. So if you have a zero vector here and a zero vector here, when I multiply by that, then I'm going to get that X would be 0, which I don't want. I don't want the vector to be 0. So we have to ensure that or no, I should say this coefficient matrix over here is singular. So since we don't want the trivial solution, then A minus lambda I must be singular. Well, how does that help? Well, this is where we pull from what we know about determinants. And we would say for this matrix, right? And it is a matrix, right? It's just a little strange because it's got this lambda and the I here. But this matrix, the only way it's going to be singular is if its determinant is equal to 0. So this implies that the determinant of A minus lambda I must be equal to 0. And then this gives me another equation, but this is not like a vector equation. This is really just a polynomial equation, right? Because remember, after finding the determinant using whatever method we think works for finding determinants, and we're going to set it equal to 0, we're probably just going to get some kind of polynomial equation, and we're going to find its roots, right? So this equation here is extremely important. It even has a name to it, and part of its name is should remind you of something we said in the previous video. This equation here is called the characteristic equation of our matrix or of our linear transformation, right? And what does this equation tell us is that the roots or the solutions are the eigenvalues. Because notice, in this case, the only thing we don't know is the lambda, right? So these are going to be the eigenvalues of our operator or of A, right? And then just one more thing here, the determinant, so just the left-hand side, let me use this color here. So just this now, if you look at that determinant, and we will look at this in detail in a second, if you look at that determinant, that's referred to as the characteristic polynomial, right, of the matrix A, right? And then what happens is, so we're going to figure out the eigenvalues first based on this characteristic equation, and then for each of the eigenvalues that we find, we have to go back here. So now that we know the lambdas, we would then be able to solve the homogeneous system, right? And let me just remind you about another important fact about the homogeneous system. Since we're saying that the coefficient matrix can't be invertible, it cannot have a unique solution. And if you think about the trichotomy, right, the three possibilities for a linear system, it's either inconsistent when there's no solution, that's not going to be the case. Either unique, that's not going to be the case either, because we're saying that the coefficient matrix isn't going to be invertible. So then that leaves what? Infinitely many solutions. So that means for each eigenvalue, we should get infinitely many eigenvectors. That's pretty cool. All right, so let's see how this works. Now, as we've seen with many of the matrix operations, right, and I'll put this in the category, it's just a little bit more involved, but of all the matrix operations that we've done before, every time we do it with a 2x2 matrix, we see something nice, like a nice pattern, something that is easily like memorizable, if that's a word. So let's actually see what the characteristic polynomial of a 2x2 matrix is, right? So let's do this for a 2x2, and then what we can do is then revisit our matrix from the previous video and actually find completely all the eigenvalues and eigenvectors, basically all the eigenpairs, right? So let's do this. But let's just look at a generic 2x2 matrix. So little a, b, c, d. Then let's write down the a minus lambda I. So then a minus lambda I, that's equal to our little a, b, c, d minus lambda times the 2x2 identity, which is 1, 0, 0, 1. And then if I distribute the scalar and then do my matrix subtraction, if you will, this is what we're going to end up with. A minus lambda, and then b minus 0, and then c minus 0, and then d minus lambda. So if you look at it, that left-hand side there, even though it looks complicated, basically what happens is you just end up subtracting lambda from the elements on the main diagonal. Now let's write down the determinant. Now, because it's going to be a polynomial and it's going to be in terms of lambda, we tend to use this notation for it. So p of lambda is just the notation that we use for the characteristic polynomial, no matter if it's 2 by 2 or 20 by 20, same p of lambda. But this is now the determinant of what we just wrote down, the a minus lambda, and then b, and then c, and then d minus lambda. So if we go ahead and use our formula, which we obviously have a nice formula for the determinant of our 2 by 2, it's the quantity a minus lambda times the quantity d minus lambda, and then minus bc. And let's go ahead and write this. Let's kind of expand this product and put this polynomial, this will be a polynomial in terms of lambda. Let's put it in the standard form. So we're going to have a lambda squared, and then as far as the terms that have just a lambda, we're going to have a negative a lambda and then a negative d lambda, and then we'll have a times d, so that's ad, and then minus bc. Now you might actually have started to recognize certain key things, right? But let's, before we do our mic drop moment, let's factor out a negative lambda. So I'm going to put a negative in front here, and then that leaves a positive a plus d, and then I'll take the lambda out on that side, and then plus the ad minus bc. And what we see here now are two important numbers associated with a 2 by 2 matrix. We know that a plus d is the trace of the original matrix. And of course, we know that AD minus BC is the determinant of the original matrix. So here's a very useful formula for the characteristic polynomial of a 2 by 2 matrix. It's lambda squared minus the trace of A times lambda plus the determinant of A. And whenever I am doing an eigenvalue, eigenvector problem, if our matrix, right, if our transformation is from R2 to R2, which means our standard matrix is going to be a 2 by 2, I just jump right into this equation and start solving for lambda. All right. So this is a really useful equation that I recommend start committing it to memory. All right. So now let's get back to the example that we started in the previous video. So let me just kind of remind you of what that was. So here's our transformation, and it took our vectors, and let me just write down the matrix. Again, nothing really special about this one, but it's 3, 1, negative 4, 8 times v. All right, so let's write down the characteristic polynomial for this. So our p of lambda, using our formula, it's going to be lambda squared minus, now the trace of this lambda is 3 plus 8, right? Just adding the elements on the main diagonal. And then plus the determinant, and the determinant is 3 times 8 minus 1 times negative 4. So we end up, if we put this and kind of simplify, we end up having lambda squared minus 11 lambda plus 28, right? So there it is. And of course, the next step now is we're going to find the roots of this, right? Because that's what's going to give us our lambdas. So if p of lambda is equal to 0, this quadratic looks nice. We can factor it. It's lambda minus 4 and lambda minus 7 is equal to 0. So there you go. We found our two special scalars. I'll just call this one lambda 1, call this one lambda 2. And we saw this one where we saw the 4, where it took the vector 1, 1 and made it 4, 4. We didn't see the 7, 7, or we didn't see the one that scales things by 7. But what we can say just at this step is this particular linear operator, there are certain special vectors, and we're going to see that there are infinitely many of them, where whenever they're transformed by this operator, they either they get multiplied by a factor of 4 or by a factor of 7. And what's remaining is we want to know which is which. All right. So what we have to do for each of the lambdas now is to go back to that homogeneous system, right? So when lambda is equal to 4, remember what we now know is this. I'm going to put my 4 in there, and then we have this homogeneous system to solve. So I'm just, since we're now going to solve a linear system, I'm going to jump right into the augmented form. And what we're going to be doing is subtracting lambda, which in this case is 4, from each of the elements on the main diagonal, and then augmenting it with the column of zeros. So if I do that, I end up getting -1, 1, and then -4, 4, and then here is our homogeneous system, right? Now you can see what's going to happen. We can clearly see that row 1 and row 2 are scalar multiples of each other. So it shouldn't be hard for you to see that if you put this in RREF, all you would do is you'd multiply the first row by -1, and then you'd use that row, and then you'd be able to eliminate everything in the second row. So it looks like this, right? And then I'm just going to use like x1 and x2 just for the components of the eigenvector, because I want to refer to the eigenvectors as like v1 and v2, right? So in this case, our x2 is going to be a free variable, so it looks like that. And then x1 minus t is equal to 0, so x1 is equal to t. So here is the eigenvector that now corresponds to a lambda of 4. So our v1 is the vector, any vector of this form, t. And remember, our vector 1, 1 fits this form, but what the algebra here is showing us is not just the vector 1, 1, but the vector 2, 2, 3, 3, -5, -5 would always work. And what we can do is, if we can write this using the scalar multiplication. So this actually shows us that any scalar multiple of the vector 1, 1 is an eigenvector that's associated with the eigenvalue of 4. So then I like to write the eigenpair like this. So the eigenpair would be 4, and then I'll put this right here. But the important thing to note, it's not just 1, 1, but any scalar multiple, basically non-zero scalar multiple, right? So in here, because we are restricting, what I should add right here is just say that t is not allowed to be 0, because we don't want the 0 vector, right? But all other scalar multiples of 1, 1, right, will be an eigenvector. And we can actually say that 1, 1 is a basis for the eigenspace that's associated with lambda equals 4. So you can even throw the basis language in there as well, right? And then, yeah, so let's wrap this up, and let's look at the second case when lambda is equal to 7. So now our homogeneous system is going to be the original matrix minus 7 times the identity times our eigenvector. That's going to be equal to 0. And if we do the same thing, just subtract 7 from the entries on the main diagonal, what do we end up getting here? It looks like -4, 1, and then -4, 1, and then of course it's always going to be homogeneous, so we have this. Yeah, so now if we wanted to put this in RREF, you know, and maybe it's not entirely necessary, but again, you might be very used to that. If you want to put this in the RREF, multiply the first row by -1/4, and you'll have this. And then that will allow you to eliminate the bottom row, and same thing, this is our free variable, so it looks like that. And then our x1 is just going to be 1/4 of t, right? Again, let me specify that t can't be 0. So then the eigenvector that's associated with the second eigenvalue is of this form. Oh, I forgot my t. So it is 1/4 t, and then t. And then if we wanted to, we could say that, yeah, all scalar multiples, non-zero scalar multiples of 1/4 of 1 is an eigenvector associated with lambda equals 7. So in this case, the eigenpair is 7 comma 1/4 1. Now, if you don't want to have like fractional entries in your eigenvector, because you can take any scalar multiple you want, you could use, let me just write this below here as we wrap up. If you wanted to use something like 1/4, you could certainly do that. That would work, right? Any scalar multiple will work. So now we've found all the eigenpairs of our this linear operator from R2 to R2. And then going forward, the question is, what else can we do with this? Are there any other properties? Anything that might be of use as far as finding the eigenpairs? And they're certainly very, very useful. And in subsequent videos, we're going to continue exploring and going a little bit deeper into understanding these interesting vectors and scalars. Hope to see you in those videos.